Far beyond the coastline, where the ocean erases every trace of land, there exists a world built for endurance, precision, and survival in complete isolation. It is not a vessel built for transport. It is a permanent offshore industrial city, extracting, processing, storing, and exporting crude oil directly from beneath the ocean floor. These reservoirs remained hidden and unreachable for most of human history, locked inside porous rock formations, deep beneath layers of sediment and time. When the reservoir is reached, completion systems are installed, including steel casing, cement barriers, and safety valves that convert the well into a controlled production pathway. Risers connect the seabed to the FPSO, carrying production upward through flexible structures designed to withstand constant motion caused by waves and currents. Each phase of separation is monitored by dense sensor networks that track pressure, temperature, and flow composition in real time across every processing module. These flow lines remain active regardless of surface conditions, ensuring uninterrupted energy transfer from reservoir to production system above the ocean. On the surface, the vessel continues to respond to subtle ocean movement, translating wave energy into controlled structural motion rather than resisting it directly. As environmental conditions shift, structural loads are redistributed across the hull and mooring system to maintain balance and prevent excessive stress concentration. Even minor changes in pressure or temperature are immediately compensated through automated adjustments that preserve system equilibrium. Cloud formations grow denser and more structured, indicating shifting pressure zones that slowly influence wind patterns across the offshore field. The FPSO does not wait for conditions to worsen. It begins adjusting operational parameters in advance to maintain equilibrium under evolving environmental stress. Operators observe updated forecasting models that simulate potential storm development and its possible impact on offshore infrastructure. This engineered flexibility ensures that production remains stable, even as mechanical loads gradually begin to fluctuate more frequently. These early wave interactions are not yet dangerous, but they represent the beginning of a broader environmental transition. This redistribution of operational stress is part of the system's core design, allowing it to remain stable under changing external forces. Inside processing units, automated systems maintain optimal separation efficiency, despite gradual shifts in incoming fluid composition. Wind intensity increases gradually, creating stronger surface friction that starts shaping longer and more energetic wave formations across the field. Production continues, but with heightened operational awareness as systems prepare for potential load redistribution across processing and structural networks. Control systems adjust internal distribution of load across processing modules, ensuring no single subsystem becomes overstressed during environmental escalation. The vessel maintains stability through continuous feedback loops that adjust mooring tension, processing loads, and subsea flow regulation in real time. Processing units maintain output stability as internal automation compensates for external fluctuations in feed composition and pressure dynamics. The FPSO responds through engineered motion, allowing controlled displacement while maintaining stability through its mooring system and structural load distribution. Subsea systems remain active, transporting hydrocarbons through risers that flex continuously in response to increased surface motion and structural displacement. The FPSO maintains operational continuity through dynamic adaptation, redistributing loads across multiple systems to prevent localized structural stress accumulation. Every subsystem operates under heightened supervision, with continuous data integration, ensuring that no deviation goes undetected or uncorrected. This is the highest stress point of offshore operation, where engineering design is tested against the most extreme environmental conditions encountered at sea. The vessel maintains stability not through stillness, but through continuous adjustment to every changing force acting upon its structure. The FPSO maintains controlled stability throughout this transition, continuing reduced production while environmental forces gradually lose their extreme intensity. As conditions stabilize, internal systems begin recalibrating, restoring optimal efficiency in compressors, separators, and processing modules. Production rates are gradually increased under controlled conditions, ensuring that system load remains balanced during the recovery phase. Control rooms maintain structured oversight, ensuring that recovery progresses safely across all mechanical, structural, and subsea systems. Subsea infrastructure continues functioning without interruption, demonstrating the long-term resilience of deep-water production networks. This phase represents controlled recovery, where offshore systems transition from emergency adaptation back to optimized production stability. Control systems shift fully out of recovery mode, returning to standard monitoring while maintaining continuous awareness of environmental variability. Subsea flow lines continue uninterrupted transport of hydrocarbons, demonstrating the long-term resilience of deep-water production architecture. Sensor networks continue to analyze system performance, comparing post-storm behavior with baseline operational models for accuracy validation. Control rooms maintain structured oversight, ensuring continuous synchronization between production output, storage capacity, and export readiness. Environmental influence remains constant but manageable, requiring ongoing adaptation rather than emergency response or structural intervention. This phase represents post-event stabilization, where the system consolidates performance improvements derived from real-world operational stress exposure. Production systems operate in perfect synchronization, where thousands of interconnected components function as a single continuous offshore structure. Control rooms maintain full oversight of global operations, where engineers and operators coordinate real-time adjustments across all production systems. Flexible offloading systems ensure safe transfer between moving vessels, maintaining stability through continuous monitoring of pressure, flow, and motion dynamics. Engineering systems evolve constantly, adapting to environmental conditions and operational feedback collected over years of offshore performance. Every storm, every cycle of production, and every operational adjustment becomes part of a growing legacy of offshore engineering knowledge. The balance between nature and engineering defines its existence, where constant adaptation ensures survival and productivity in a dynamic environment. Nothing here is temporary. Every system is engineered to operate continuously under extreme offshore conditions, where failure is not an option but a risk constantly managed. Hundreds of people live and work on board in continuous shifts, maintaining systems that must operate without interruption in one of the most isolated environments on Earth. Modern offshore engineering changed this reality by developing technologies capable of imaging, drilling, and producing from extreme deep-water environments. What begins to flow upward is not pure oil, but a complex mixture of hydrocarbons, water, gas, and sediments moving under extreme pressure from deep underground. When production reaches the FPSO, it enters massive separation systems, where gravity begins the first stage of processing by dividing gas, oil, and water. Inside the FPSO, separation systems continue the transformation of raw production into structured flow streams under constant pressure and controlled environmental conditions. The FPSO operates as a closed-loop industrial environment where extraction, processing, and storage occur simultaneously without interruption or downtime. At the seabed, subsea trees regulate flow with precision valves that can adjust production rates or completely shut down wells if safety conditions require it. Every deviation from expected performance is instantly flagged, allowing rapid response before minor fluctuations can develop into operational instability. Mooring lines anchor the vessel in position while allowing limited movement, creating a controlled range of motion essential for offshore operational safety. Each system is linked through integrated control architecture that ensures synchronization across production, safety, and structural monitoring networks. This is the foundation of offshore engineering, maintaining equilibrium in an environment that is never truly stable. Onboard sensors detect subtle variations in barometric pressure, registering environmental changes long before they become visible to the human eye. At this stage, the ocean remains operationally manageable, but it is no longer fully calm, signaling the beginning of a new environmental phase. Subsea systems remain stable, continuing to deliver hydrocarbons from deep reservoirs through flow lines that are unaffected by surface atmospheric change. Control systems integrate these changes into real-time models that adjust operational parameters to maintain safe production thresholds. Offshore operators maintain continuous observation, knowing that early detection of environmental shifts is critical for safe industrial continuity. Even minor fluctuations in wind speed are translated into measurable mechanical responses across the vessel's structural framework. The FPSO enters a phase of heightened awareness, where stability is maintained not through inertia, but through continuous predictive adjustment. The FPSO responds through controlled adaptation, maintaining position and operational balance while absorbing increased environmental energy through its mooring system. As wave energy increases, the vessel experiences deeper and more pronounced motion cycles that remain within designed operational tolerances. Despite these changes, production remains continuous, supported by automated systems that constantly recalibrate flow rates and processing efficiency. Operators remain fully engaged in continuous observation, ensuring that any deviation from expected behavior is immediately analyzed and corrected. The FPSO remains in a state of controlled escalation, where environmental force increases but is continuously balanced by engineered adaptation. Wave height increases significantly, and the ocean surface loses its previous structure, becoming a chaotic and continuously shifting field of force. Production continues under strict adaptive control, with flow rates automatically adjusted to maintain system stability under peak environmental stress conditions. Despite extreme conditions, all critical systems remain synchronized, ensuring that production, safety, and structural integrity operate as a unified network. The vessel moves in deeper cycles, absorbing ocean energy while maintaining controlled positioning through tensioned mooring lines anchored to the seabed. At peak intensity, the ocean behaves as a fully active force system, where energy is continuously transferred between wind, water, and structural interaction. Despite the intensity, the system remains fully functional, demonstrating the resilience of integrated offshore production architecture under sustained load. This phase represents the absolute convergence of engineering precision and natural force, where offshore systems operate at their maximum adaptive capacity. As peak storm intensity begins to decline, the ocean slowly transitions from chaotic energy fields into more structured and predictable wave systems. Operators closely observe environmental normalization patterns, ensuring that no secondary instability emerges as the system transitions toward recovery. Despite extreme environmental exposure, all critical systems remain operational, demonstrating the structural resilience of offshore engineering design. Automation systems adjust flow distribution to restore efficiency, while preventing sudden mechanical or pressure imbalances across processing units. This information is integrated into operational models, improving predictive accuracy and strengthening future offshore response strategies. Even as calm returns, continuous monitoring ensures that all systems remain prepared for future environmental variability and offshore risk exposure. Operators confirm system stability through comprehensive checks across all production, safety, and subsea infrastructure networks. Inside processing modules, compressors and separators operate at optimal efficiency, recalibrated after extended exposure to high-stress environmental conditions. This data becomes essential for refining predictive models and improving future offshore operational strategies under similar conditions. The FPSO resumes its long-term operational rhythm, balancing extraction, processing and storage within a continuously adaptive system. The vessel continues to operate as a floating industrial ecosystem, designed for permanent interaction with one of the most dynamic environments on Earth. Continuous monitoring ensures early detection of any anomalies, preserving long-term stability and preventing future operational disruptions. The vessel stands as a floating industrial ecosystem, continuously extracting, processing, storing and exporting energy from deep beneath the ocean floor. Every subsystem on board the FPSO operates under continuous monitoring, ensuring that production efficiency and structural integrity remain within optimal parameters. Each export cycle connects offshore production to global energy networks, transferring millions of barrels across the ocean to refineries worldwide. The entire system functions as a continuous loop, where extraction, processing, storage and export operate without pause or interruption. This accumulated experience strengthens future designs, improving resilience, efficiency and safety in the next generation of offshore systems. And in the endless blue of the open sea, the FPSO stands as a silent, continuous engine of global energy transformation. At first it appears to be a ship alone in the ocean, but as distance closes, that illusion breaks, revealing a massive industrial structure rising above the sea surface. Engineers, operators, technicians and safety specialists all function as part of a single integrated system where every decision affects the stability of the entire facility. Before drilling begins, seismic surveys send acoustic waves into the Earth and analyze their reflections to map hidden geological structures beneath the seabed. At the seabed, subsea trees regulate flow, monitor pressure, and provide emergency shutdown capability, acting as the primary control interface between reservoir and surface systems. Far below the vessel, subsea pipelines continue transporting hydrocarbons through kilometers of engineered flow lines designed to withstand pressure, corrosion, and constant motion. Control rooms remain the operational core of the system, where engineers oversee thousands of variables simultaneously through integrated digital monitoring platforms. This balance between restraint and flexibility defines the engineering principle that allows floating production systems to operate in deep water environments for extended periods. The FPSO does not operate as separate machines, but as a unified organism of industrial processes working in constant coordination. Far from the stability of the control rooms, the ocean begins to show early signs of atmospheric change as distant weather systems reorganize across the horizon. Wind patterns shift gradually across the ocean surface, altering wave formation dynamics and introducing subtle irregularities in sea behavior. Production continues without interruption, but with increased awareness of external conditions that may require future operational adjustment. Risers respond to this change with flexible movement, compensating for increased oscillation between seabed infrastructure and floating production unit. As conditions evolve, the FPSO adjusts internal flow distribution to ensure that no single processing line experiences excessive load variation. Gas, oil and water separation continues uninterrupted, supported by continuous calibration of pressure and temperature conditions. Operators observe the shift in real-time data streams, where small fluctuations in pressure and wave height begin forming consistent upward trends. This movement is not instability, but engineered response, where the structure is allowed to move in controlled patterns to dissipate external force. Inside the FPSO, all critical systems remain synchronized, ensuring that operational integrity is preserved across mechanical, electrical, and digital layers. The ocean now exerts a stronger influence on vessel motion, requiring tighter coordination between structural response and production system stability. This phase represents the transition toward peak offshore stress conditions, where system responsiveness becomes critical to maintaining full operational continuity. Inside control rooms, all monitoring systems shift into maximum awareness mode, tracking real-time changes in structural stress, production flow, and environmental impact. The interaction between vessel motion and subsea tension becomes more intense, requiring precise coordination between mechanical flexibility and flow stability. Wave systems now interact in complex patterns, creating overlapping forces that challenge traditional predictability of offshore environmental behavior. The FPSO does not resist these forces directly, but maintains equilibrium through controlled flexibility and distributed structural response. Even at peak environmental stress, production remains active, though carefully regulated to ensure all systems operate within safe design parameters. The vessel continues to move with residual ocean energy, but motion cycles become less extreme and more consistent with engineered design expectations. The FPSO re-enters a phase of operational normalization, where stability is achieved through continuous monitoring and adaptive system calibration. The recovery phase reinforces the importance of adaptive engineering, where systems evolve through real environmental exposure and operational feedback. Production rates are restored gradually to optimal levels, ensuring that no sudden load transitions affect system integrity after the storm cycle. The FPSO demonstrates full recovery capability, returning to stable production while retaining all data collected during extreme environmental exposure. Human expertise remains central to system performance, ensuring that engineering decisions align with real-time operational and environmental conditions. The offshore system evolves through each cycle, becoming more resilient and efficient as it adapts to recurring environmental challenges. As full operational stability returns, the FPSO resumes its complete industrial rhythm in the open ocean, surrounded by vast and uninterrupted sea in every direction. The ocean remains present in constant motion, but now serves as a stable operational environment rather than a source of disruption or extreme stress. As storage levels rise, export operations are prepared through precise coordination of shuttle tanker scheduling and environmental condition analysis. Maintenance and inspection routines ensure long-term reliability, preserving structural integrity across all mechanical and subsea infrastructure. It remains permanently stationed in open ocean, isolated from land, yet fully connected to global energy demand and supply chains. This is an FPSO, a floating production, storage and offloading unit designed to remain stationed over deep-water oil fields for years or even decades without returning to shore. But the story does not begin on the surface. It begins thousands of meters below the ocean floor, where hydrocarbons formed over millions of years under extreme geological pressure. Every meter drilled produces critical data including pressure, temperature, and rock composition, transforming the subsurface into a continuously analyzed environment. Flowlines transport production across the ocean floor, while umbilicals deliver power, chemicals, and communication signals that allow continuous remote control of subsea infrastructure. Gas rises naturally within large separator vessels while water sinks, and stabilized crude oil is extracted as the central output for storage and export. Umbilical cables accompany the pipelines, delivering electrical power, hydraulic control, and chemical injection necessary for subsea well management and stability. This engineered flexibility allows the FPSO to remain stable, even as wind, currents, and wave systems continuously alter the surrounding environment. The ocean outside remains unpredictable, yet the FPSO is designed to function as a stable industrial system within that unpredictability. Inside, processing modules, compressors and pumps operate continuously, maintaining flow stability even as input conditions fluctuate with reservoir dynamics. As production continues, stability becomes a dynamic target rather than a fixed state, constantly maintained through continuous feedback and correction. These early indicators are continuously analyzed by predictive systems designed to anticipate operational impact across production and structural stability. Inside the FPSO, monitoring frequency increases as control systems begin tracking weather evolution with higher resolution data inputs. However, the relationship between surface motion and subsea tension begins to shift subtly as wave energy slowly increases. The ocean surface becomes slightly more irregular, with longer wave patterns beginning to intersect and form complex energy distributions. The ocean remains the dominant environmental force, but its behavior is now actively monitored as a variable influencing every aspect of production. As offshore conditions continue to evolve, the ocean begins transitioning from early instability into a more aggressive and force-driven system of motion. Inside control rooms, monitoring frequency increases as predictive models begin simulating more complex weather scenarios with higher uncertainty ranges. Flowlines continue transporting hydrocarbons without interruption, demonstrating the resilience of deep-water engineered systems under evolving ocean conditions. Rain begins to appear intermittently across the horizon, driven by developing atmospheric instability that signals further environmental intensification. This dynamic equilibrium allows the FPSO to function as a stable industrial platform, despite increasing ocean variability and atmospheric pressure shifts. Despite rising complexity, the system continues to operate within engineered safety margins, demonstrating the resilience of offshore design principles. The offshore environment now enters its most critical phase, where wind, waves, and atmospheric pressure converge into a unified system of extreme ocean energy. Operators observe rapid fluctuations in wave data and wind intensity, while predictive models continuously update risk scenarios for offshore operational safety. Rain and wind now dominate the visual environment, reducing visibility across the offshore field while increasing the mechanical load on exposed structures. Inside processing modules, automation systems adjust compressor performance and separator efficiency to maintain stable output under fluctuating input conditions. Control rooms continue to function as the decision core, coordinating responses across thousands of variables in real time with no interruption in communication. Wind speed decreases incrementally and rain intensity weakens, allowing visibility to gradually return across offshore operational zones. Subsea production remains uninterrupted, with flow lines and risers continuing stable transport of hydrocarbons despite reduced surface turbulence. Every component is reviewed through sensor data analysis, comparing real-time performance metrics with baseline operational standards. Data from the storm event is analyzed in detail, providing critical insights into system performance under extreme environmental stress. The FPSO gradually returns to its primary operational rhythm, balancing production, storage, and export readiness under stabilized conditions. The vessel continues forward in equilibrium, fully functional and stabilized after one of the most demanding operational cycles of offshore production. As offshore conditions return to near normal stability, the FPSO resumes full operational continuity across production, processing, and storage systems. Risers stabilize under reduced motion conditions, allowing smoother transfer of reservoir fluids from seabed infrastructure to surface processing systems. The ocean environment stabilizes further, though subtle atmospheric changes continue to influence vessel motion and operational planning. Every subsystem operates in coordination, reinforcing the principle of integrated offshore engineering where no component functions in isolation. The FPSO now functions at full capacity again, maintaining equilibrium between production demands and environmental forces without disruption. The FPSO continues its uninterrupted cycle of production, fully restored and stabilized after completing a complete offshore environmental stress event. Subsea reservoirs continue feeding hydrocarbons through engineered networks that stretch across kilometers of seabed before reaching the floating facility above. Storage systems accumulate stabilized crude oil in massive integrated tanks designed to maintain balance even under changing load and environmental conditions. Once transfer is complete, the FPSO immediately returns to production mode, maintaining the uninterrupted cycle that defines offshore energy systems. The FPSO is not simply a machine, but a fully integrated industrial environment operating continuously in one of the most extreme locations on Earth. From the surface, the FPSO appears distant and silent, but within it operates a vast network of continuous industrial activity. As long as energy remains beneath the ocean floor, these floating systems will continue to operate, evolve, and endure across decades of offshore production. These subsurface images reveal potential reservoirs where oil and gas may be trapped, allowing engineers to plan drilling operations with high precision and reduced uncertainty. Once a viable reservoir is identified, offshore rigs begin drilling through kilometers of water and rock using highly controlled directional drilling systems. Automation systems continuously adjust internal parameters to maintain efficiency, ensuring that fluctuations in incoming reservoir fluid do not destabilize production quality. Every component of this network is designed for long-term autonomy, operating for years without physical intervention while maintaining real-time communication with the FPSO. Production adjustments are made continuously, not as isolated actions, but as part of a constantly evolving optimization process driven by real-time data. Subsea infrastructure remains stable, though the interaction between surface motion and riser flexibility becomes increasingly dynamic and continuous. The ocean surface becomes more fragmented, with intersecting wave patterns, generating irregular energy fields that challenge visual and structural predictability. As environmental stress increases, safety protocols shift toward higher sensitivity thresholds, preparing the system for potential controlled reduction if needed. Even minor increases in wave height translate into measurable changes across the FPSO's structural load distribution and motion profile. Safety protocols escalate automatically, with emergency thresholds actively monitored to prepare for controlled reduction if environmental limits are exceeded. Operational decisions are executed in real time, balancing production continuity with strict safety constraints to preserve long-term system integrity. Control systems shift from maximum alert mode back toward high vigilance monitoring, maintaining readiness while reducing emergency response sensitivity. Maintenance teams initiate preliminary inspections of external structures, carefully assessing potential stress impacts caused by peak storm conditions. The ocean continues to settle, but never returns to complete stillness, maintaining a constant influence on vessel dynamics and operational stability. Environmental forces remain present, but significantly reduced, allowing offshore systems to resume standard operational rhythms. The ocean remains active but significantly calmer, with wave systems returning to longer, more predictable patterns that reduce structural stress on the vessel. Maintenance teams complete detailed inspections of structural components, confirming that no critical damage occurred during peak storm activity. Over time, accumulated operational experience strengthens system reliability, improving both efficiency and resilience across offshore production cycles. Far beneath the surface, geological formations continue releasing hydrocarbons formed over millions of years under extreme pressure and temperature. It represents the convergence of engineering precision, environmental adaptation, and human expertise working together in real-time offshore conditions.